Thank you very much. Let me just say that it's a great honor for me to speak at this conference. And like pretty much everything in geometry and physics in the last 20 years, this talk will be greatly influenced by work of Maxime and Jan. So this is about a connection between Donaldson-Thomas invariants and character varieties. So to be more precise, it's about especially the motivic Donaldson-Thomas theory developed, as I said, by Maxime and Jan. And a conjecture formulated by Hausel, Letelier, and Rodriguez-Villegas on the cohomology of character varieties of smooth projective curves with marked points. So for the first, 15, 20 minutes, maybe I'm going to just set up the stage and review this conjecture and try to write down the formula they propose, which is a truly beautiful and remarkable formula. So, okay, so right. So let's set the stage. So C is a smooth projective curve over complex numbers. The genus is gonna be G. We're gonna have two marked points on C. P and infinity, P, of course, distinct marked points. This is not a serious restriction. This is mostly for presentation purposes. I don't want to get tangled in too much notation. And gamma P and gamma infinity are the corresponding generators of the fundamental group of the punctured curve. And then we need to specify some more data. So we're going to have to fix a diagonal matrix. It's all complex numbers, so I'm not going to keep writing complex numbers. A diagonal matrix, an invertible diagonal matrix. Mu is going to be a partition of R. This is the partition that determined by multiplicities of eigenvalues. Eigenvalues of lambda. So you determine a partition of R. And now finally an integer E coprime with R. So E is just some integer coprime with R. OK. So what is the character variety then? The character variety is going to be, roughly speaking, the moduli space of conjugacy classes of representations of this fundamental group into GLR. OK, so we set C E lambda to be, as I said, the moduli space of Holmes from the fundamental group of the punctured curve into GLR, sending gamma P to the conjugacy class of lambda, and sending gamma infinity to a central element, 2 pi square root of negative 1 E over R. And all this is modular conjugation. So this is a major object of study. The topology of this character varieties is very, very interesting. Now we have a theorem here. So in order to make the notation short, I'm going to refer to the work of Hausel, Letelier, and Rodriguez-Villegas as HLRV, saying that for sufficiently generic lambda, CE lambda is a smooth quasi-projective variety of course, over complex numbers. And furthermore, a consequence, or empty, possibly empty, but if not empty, it's smooth and quasi-projective. And if you compute its dimension, you find out it's some formula, but it depends only on the partition mu. So it has some formula I'm not going to write down, but it's only dependent on the partition mu. All right, so now what are we going to study in this context? It's the some kind of weighted Poincare polynomial of this variety. So what I want to study, what I should say HLRV studied, was they looked at, since this variety is non-compact, it has a non-trivial weight filtration and cohomology due to Dulin. So, and they studied so we have the cohomology of this variety C has a weight filtration, W. And you can define, the compactly supported cohomology it still has a weight filtration. So we can define some kind of weighted Poincare polynomial by the following formula. P compact of this, it's a function of two variables, formal variables u and t. It's the sum over the dimensions of the graded pieces of the wave filtration on HK compact, weighted by this monomial, which looks a little bit funny because it looks like I need to take a square root of u. But then furthermore, but in fact, this turns out to be a polynomial. So there are further results, again, of HLRV saying that this is in fact a polynomial of so this PC, it's a polynomial of u and t. So only even I occurs in that formula. And furthermore, it depends only on mu. So on the partition mu. So a lot of data that I specified before doesn't actually enter in the, there's no dependence on the specific values of the eigenvalues, for example. So we can call it, so we can denote it, we can just write P of mu ut without any ambiguity. OK, so now finally let me get to the point of writing this conjecture they formulated. So the question was to determine all these polynomials for all possible values of the rank and all partitions mu. And they wrote a beautiful formula, which I want to write down here and leave it on the blackboard for the rest of the talk. So this is the HLRV conjecture. So it's written in a which is in a way that's really very, very suggestive to a physicist. It's written like saying that the partition function of some system is the exponential of a free energy. Well, I'm using these names. They certainly did not use this terminology, but for a physicist, it's very natural. So first of all, let me write this here. So what appears in the exponential, it's a platistic sum. So it's a sum over all partitions. It's a sum over k greater or equal to 1, 1 over k. And then we have what we have here. And let me write the sum in here. W to the minus k d mu. Z and W are going to be some formal variables, purely formal variables. So the k divided by 1 minus z to the k, W to the 2k minus 1, m mu of x to the k. OK, z, w, and x are formal variables. X is actually an infinite set of formal variables. The m mu's are the monomial symmetric functions. So this is what appears in the exponential.
Is the dependence on genus?
Oh, I'm sorry. Yeah, you're absolutely right. There is dependence of genus in here.
Hidden genus, yeah.
Oh no, it's because I just forgot the p. I apologize. I need to sorry. I need to have a genus, and it's in the polynomial will depend on the genus certainly. I apologize. This was just an empty formula what I wrote there. OK, so yeah, so depends on G. Well, it's OK. So yes, depends on G. OK, good. So this is one side of the formula. And then what is the other side? The other side, it's the way.
What's mu?
It's the monomial symmetric functions associated. Mu is the monomial symmetric function for the partition mu, and x is just some infinite set of variables. So you just imagine x is just x1, x2, ... So it's all formal variables here. All right, so this is one side. The other side, quite remarkably, the other side is just a pure combinatorial object. It's a sum of Gannovo partitions, but other partitions. I mean, the same partitions, but they have a different nature. So there is a rational function I'm going to write in a minute associated to any partition, and then it's weighted by some by modified Macdonald polynomials. So I'm gonna explain all these quantities here. First of all, this is easy to write. It's some rational function, which is the product over all boxes in lambda of z minus 2a plus 1, which a is the arm length of a box, minus w to the 2l plus 1 to the 2g. L is the leg length of a box, divided by z to the 2a plus 2 minus w to the 2l, z to the 2a minus w to the 2l plus 1. So indeed, this is, as you see, it's explicitly dependent on g. So let me just write this in words before I explain what these functions are. So h lambda twiddle is, they are called the modified Macdonald polynomials. Now, I know very little symmetric function theory, so I couldn't give you a definition of that function over there. Fortunately, I don't have to give you a definition in symmetric function theory. What I am going to do is give you a geometric construction for these functions, which is due to Heyman. Okay? So for our purposes, it's much more illuminating to think of them, to employ the geometric construction for this modified Macdonald, which is a result of Heyman. And it involves the Hilbert scheme of points in C2.
What means succession generic here? How effective is this? Is it to complement finitely many points or many points?
There is a precise condition that I'm not remembering, but there is a very specific condition here. I think it might be complement of high-dimensional subspaces, not just points. Yes, it's explicitly given in the paper. OK, so now let's discuss a little bit the modified Macdonald functions, because this is going to be important for what I have to say next. All right, so now this is, as I said, according to Heyman. So we're going to look at the following diagram. This is the symmetric product S of C2. This is it's just the Cartesian product, and this is an n factorial to 1 cover. Now here we have the Hilbert scheme, Hn of C2. And this is the Hilbert-Chow morphism, collapsing whichever cycle's there. And now we complete the square, and we get what's called the isospectral Hilbert scheme. So this is the isospectral Hilbert scheme, which is, again, it's generically an n factorial to 1 cover, but something pretty bad happens basically over the non-trivial fibers of this morphism here. And in general, this is as the scheme is not even reduced. But what Heyman proved, so there is a structure theorem. What he proved is that this H twiddle and C2 reduced, if we take with reduced scheme structure, it's irreducible and Cohen-Macaulay. And that was very important, because what he did next was to take a push forward of the structure shift here down here. And if you endow this with the reduced scheme structure, what you get down there, it's a nice vector bundle, which is known under the name of Procesi bundle. And that's really the main geometric ingredient in the construction of the McDonald polynomials. All right, so now let's let P is the push forward of O, H, and twiddle reduced. Okay, so now this turns out to be a rank n factorial vector bundle on Hn. And not only that, but it carries a fiber-wise action of the permutation group of n letters. So there is an action of Sn naturally by construction there. All right, so now the other thing we need is there is another natural action of a torus on the Hilbert scheme of points, which comes from just the scaling action on C2, the diagonal scaling action on C2. And it's very well known that if we classify fixed points here, what we get is a bunch of monomial ideal labeled again by partitions of n. All right, so now to get this McDonald polynomial, what we need to do is look at the fiber of P over a fixed point there, and look at it, and there is a simultaneous action of Sn and an action of T, and they commute again naturally by construction. So and what we learn then is that if we restrict P to a fixed point, this decomposes into a sum of characters, obviously. It decomposes over a sum over partitions. Let me write this like this. And I'm going to explain the notation. These are the irreducible representations of the symmetric group. And these are just representations of T. So it has a decomposition like this, which is, again, it's all natural. All right, so now finally, what is the McDonald polynomial in this context? Let me write, this is a theorem. Maybe I can write it here again due to Heyman. We have the following. I mean, this is a hard theorem, so this is highly non-trivial identity. Although, me being a physicist, I'm going to take it basically as a definition for McDonald polynomials in my case. So it's given by this following formula. Q1 and Q2 are the generators for the character lattice of this guy, of this torus, algebraic torus. This is the character, and these are the Schur functions. So as I said, this is a hard result. So it has a complicated and hard proof. But this is for us the most natural definition for this. I mean, it's not a definition, but for the purpose of this talk, it's going to be a definition. All right, so it's very intriguing that indeed these functions appear in this particular formula. And I should say that the way they arrived at this formula was by counting. So what they did was to formulate the problem over finite fields, because the character variety is defined over finite fields. And they counted rational points. And what they did is that eventually, using then the Weyl conjectures, they arrived at this formula. And they even proved a specialization of this formula, which I'm thinking sets z equals W inverse or something. So that is proven. That's a theorem.
Well, just a second. If you can't variety of point of finite field, you can count only weight, but cannot distinguish the Green cohomology.
That's what they proved. A specialization of this formula. Yeah, specialization where z equals W inverse, I think. That's exactly what happens. You turn off the cohomological degree. Exactly, yeah. And that's proven. But then, based on some symmetries and some, they conjectured this. All right, so now, as I said, me being a physicist, when I saw this formula, it looks very, very intriguing and very elegant. So I was thinking, how can I get this out of string theory? Is there any way of deriving such, not proving it, but deriving it or explaining it from string theory? And especially, how can I explain the occurrence of these guys, of the McDonald polynomials?
And how McDonald polynomial appeared in their proof?
But in their proof, what they get is a specialization of these McDonald polynomials. Because you see, that's what I'm saying. They collapse to something much simpler. So only when you write the full conjecture, then you get this two-parameter family of functions. All right. So the way this goes is by first employing another piece of mathematics which relates character varieties to the moduli space of Higgs bundles. And in this particular case, it's going to be Higgs bundles, parabolic Higgs bundles on the curve. It's another piece of beautiful mathematics, which goes back to work of Hitchin, Donaldson, Simpson, which tells us that there is a deep relation between character varieties and the moduli space of Higgs bundles. And in this particular case, we get a special flavor. I mean, we get a flavor of Higgs bundle, which has parabolic structure. So I want to say a few words about to bring the Higgs bundles in the picture and the P equals W conjecture. This is a conjecture formulated by Cataldo, Migliorini, and Hausel. Hausel and Migliorini. But it really relies on previous work, as I said, of Hitchin, Donaldson, and Simpson, which tells us basically that as a real manifold, this character variety we defined, it's actually canonically identified to a moduli space of Higgs bundle, of stable Higgs, and in this particular case, parabolic Higgs bundles. On C. So I'm going to call it H. Let's call it He lambda of C from Higgs. Hopefully, it's not going to be too much confusion between this and this H and that H. Maybe I should call it Higgs to make sure that Higgs.
What is E standing for?
E is the degree.
Oh, E is
I haven't told you the map between character variety data and Higgs bundle, but E is going to be just the degree of the bundle. So as I suspect, most people in the audience know a lot more about this than I do. Just to fix notation, what I'm talking about here is pairs E phi, where E is a vector bundle on C, and phi is a okay. So we're talking about pairs E phi, where E is a vector bundle on C, phi is an endomorphism with values in a twist of Kc by the point P. I'm just looking at a single point for simplicity. And what we need to know is that we have to specify a flag of type mu at P, in the fiber EP. And then we also have some parabolic weights. Well, okay, I'm being a little bit sloppy here, but I just don't want to get bogged down in details. What I am going to do here basically is take a special. I'm going to take the lambda to be something like a diagonal of pure phases, e to the 2 pi I square root of minus 1 alpha 1 and so on, and the parabolic weights are going to be just these numbers that appear there. So this qualifies as sufficiently generic according to the definition. I mean, I can make this sufficiently generic.
And from flags, you should also order somehow in terms of partition.
You're absolutely right. I'm being really sloppy here. Yeah, what you have to do is take the multiplicity of the first guy, and that's the dimension of the first quotient, and so on. Yes. So I'm being sloppy. I could go through the details, but yeah, I should say the type ordered mu with the natural order given by the order of eigenvalues, and then maybe that would make it. And then there is a notion of parabolic slope, and the notion of slope stability. It's all standard, and you have slope stability for these guys, and you get a smooth moduli space, which is this Higgs moduli space. E lambda c. So this is again, it's a smooth quasi-projective variety, and as I said, it's as a real manifold, it's identical to the character variety, but the complex structures, the algebraic variety structures are very different, and that leads to this highly non-trivial conjecture formulated by Cataldo, Hausel, and Migliorini concerning what is the interpretation of the weight filtration on the Higgs side. Okay, so that's the issue. And again, without getting into too much detail, because this is really an embarrassing moment. I mean, most of the audience knows a lot more about perverse sheaves than I do. What they do is to define a perverse filtration on the cohomology of the moduli space of Higgs bundles using the decomposition theorem for the Hitchin map. So the story is that there is a Hitchin map to basically a vector space, which is obtained by taking the polynomial invariance of the Higgs field. So this maps by map H to some vector space, which I'm not going to try to write in detail. And this is the map which associates the phi trace of phi to the k, a vector polynomial invariance for 1 smaller than k smaller than r. To E phi, but yeah, you just take the polynomial invariance of phi to the k. And in this complex structure, this is a holomorphic, it's an algebraic map. And using the decomposition theorem for this, we obtain a perverse, so-called perverse sheaf filtration on the cohomology of the Higgs moduli space of Higgs bundles. And this is going to be called P, all right? And the conjecture is that basically Pi, if you set up your conventions correctly, which is a fairly subtle issue here, so set up your conventions, Pi equals W2I for all I. As I said, this was formulated by Cataldo, Hausel, and Migliorini, and they proved it for rank 2 with no parabolic structure. So that's even there, it was a hard proof. So it's proven for rank 2 with no parabolic structure. Okay, so these are the ingredients. So this is all a math story. So now what I want to do in the remaining, I don't know, most 15, 20 minutes maybe, is how this all ties together and all the pieces click together in the context of motivic Donaldson-Thomas theory. So what is the plan here? Well, we want to have...
Do they show that this conjecture implies the formula?
The conjecture certainly implies the formula. No, apologize. No, the conjecture doesn't imply the formula. The conjecture basically gives you another conjecture for where the dimensions of the W-graded pieces are replaced by the dimensions of the P-graded pieces. No, the conjecture doesn't imply the formula because this side of the formula came from, as I said, by counting points and then extrapolating from the point count. And on the Higgs side, it was checked for rank 3 by direct localization on the Higgs side, by just fixed point theorem on the Higgs side. It was checked. What was checked? What was checked was the prediction obtained from there for the Poincare polynomial. That can be checked. But for higher rank, it's getting really hard. So let me just, so what's the plan? We want to obtain some kind of derivation of the formula from, well, if you are a physicist from string theory, if you are a mathematician from Donaldson-Thomas, or I should say motivic Donaldson-Thomas theory. So motivic DT theory. So I should say that from the outset, this is not going to be a proof. But basically, what I'm going to manage to do is reduce that formula to some, so to speak, standard conjectures in DT theory. So I don't know how much time I have to explain, but that's going to be, so it's going to follow from some standard fairly standard conjectures in DT theory, but it's not. It gives you a framework for a proof. So basically, it tells you when those are proven, then this is proven too. But OK. So all right. So now what's the first step? Well, since we're talking about motivic Donaldson-Thomas theory, so what we need is to find a Calabi-Yau threefold lurking around here. So far, I've been on a curve. So everything was done on a curve. So where is the Calabi-Yau threefold in this picture? So the first step would be construction. So what I want to do first, step 1, we need to construct a Calabi-Yau threefold, X, for example, such that this moduli space of Higgs bundles is going to be isomorphic to a moduli space of Bridgeland stable pure dimension 1 sheaves. Pure dimension 1 sheaves on X. Now, this looks kind of a loose statement because, I mean, how can you Calabi-Yau? There are lots of Calabi-Yau threefolds. But fortunately, there is here we can rely on some results obtained in the literature by Biswas, Born, Greshenig, which basically gives us a machinery of identifying parabolic bundles on C are identified with just ordinary vector bundles on a root stack. Which I'm going to call C twiddle. So basically what's happening, informally, of course we can immediately write down some rigorous formulas. You take this point P here, and you excise it, and what you glue in is it's a stack basically, which looks locally like C mod mu L. You insert in a stacky point where L is just the length of the partition mu. How many parts you have in mu? So you insert an orbifold point, and what you get is it's a smooth orbifold. It's a smooth Riemann for stack, which furthermore projects naturally to C by some map rho, and this is going to be a coarse moduli space. I mean, C is a coarse moduli space for C twiddle. So and then there is some work I don't have time to review in detail, which allows me to reformulate the moduli problem for parabolic Higgs bundles on C as a moduli problem for just ordinary Higgs bundles on the root stack. And from there, the next step is to come up with a Calabi-Yau threefold. So coming up with a Calabi-Yau threefold, it's fairly easy at this point. It's kind of disappointingly easy. What you have to do is to take a fairly naive construction, which is to set, all right, I'm doing OK. All right, we set X is the total space of OC twiddle plus KC twiddle, which is, of course, I lied a little bit. This is not a Calabi-Yau it's not a smooth Calabi-Yau threefold. It's just a smooth orbifold. This is going to be a Calabi-Yau orbifold of dimension 3, and that's the setup. And then you can easily prove that, well, what you can prove, it's not quite that. What you can prove is that if you cross with A1, then the moduli space of Higgs bundles, it's isomorphic to to the moduli space of dimension 1 sheaves. But this is pretty harmless. I mean, this is pretty harmless there. All right, now, what's this? Well, we have a geometric setup. So we lifted the problem from a curve to a Calabi-Yau threefold. So this is what physicists well, it just increased dimensions. OK, so now what's the second step? Now, for physicists, I should say, once you get to this point, this moduli space of pure dimension 1 sheaves and so on, these are just the 2D zero bound states in this orbifold background. OK, so we kind of managed to reformulate Higgs bundles to identify them with supersymmetric D2D zero bound states. Now, the second step is to employ now we're looking at the motivic dt theory of x, as I said, of Kontsevich and Soibelman. And more specifically, we're going to look at specific objects in the derived category of x, which are the stable pairs considered by Pendary, Pendy, and Thomas. So, so from Pendary, Pendy, and Thomas, we know there is a counting theory for let me write upwards, for stable pairs, which means our pairs Ox to F, where this guy is pure dimension 1, sheaf, and S is generically surjective. I don't have time to get into too much detail. The construction of Pendary, Pendy, and Thomas produces a moduli space with symmetric virtual obstruction theory. So with symmetric virtual cycle, and then you can get numerical invariance. But then using the machinery of Kontsevich and Soibelman, we can actually get motivic invariance. We can get motivic invariance for such objects. And then from motivic invariance, I'm going to just specialize the polynomial invariance by taking the so-called Serre polynomial. This is, as I said, I'm summarizing a lot of mathematics in a few words, but I don't have time for saying more. I want to erase this one, sorry. OK, whatever. So from Kontsevich and Soibelman, what we get is we get motivic stable pair invariance and then you specialize the polynomial by taking the correct polynomial specialization, which is compatible with motivic decompositions. So we get polynomial invariance. And finally, we can get a partition function, which I can call Z, PT. I should say that the polynomial invariants are called refined in physics. We also saw this refined BPS states occurred in Sergei's talk. Yeah, they are very much related. It's just the background is different. So we get some partition function like this. So we get some generating function for polynomial invariance. And OK, so now the main conjecture we formulate then, the main conjecture states the following, that this side equals this side of the HLRV formula, up to a monomial change of variables. So it's not quite coming in W and Z. I have to take some combinations, but really easy combinations, like Z squared and Z over W or something like that. Nothing complicated. So this is the main conjecture. This is one of the conjectures we oh, man, I forgot. I should say this is all work with Wien Chuang, Ron Donaghy, and Tony Pantev. So this is pretty much, this is work done together with Wien, Ron, and Tony. And one of the main conjectures we formulated is this one. It's to identify this side of this identity as a refined PT partition function. All right, now what will this buy you? Well, if you combine this with the other identification of the moduli space of Higgs bundles, what you realize then, by staring at that formula, is that in fact the whole HLRV formula. So what this buys you is that so what we get from here is that if we get a diagram of identities like this, this is the exponential of HLRV, And then we have a change of variables here, and a change of variables here, the same change of variables, which identifies this side with a refined Donaldson-Thomas partition function here, or PT partition function. And this one, it's identified with a refined Gopal-Kumar-Vafa expansion. So this is refined Gopal-Kumar-Vafa expansion. Which appeared in many places in physics. So this appeared in, well, and somehow it's implicit in the original work of Gopal-Kumar and Vafa, Katz, Clem, Vafa. Then it was written explicitly for Tori, Calabi-Yau threefolds in Iqbal, Koskas, and Vafa, and more recently considered by Katz, Clem, and sorry, I forgot the full reference. So anyway, so it's considered in many places in physics. In this particular case, it's slightly exotic because we use this expansion for a non-toric orbifold. But anyway, the message here is that this reduces to, and this is one of the standard conjectures in Donaldson-Thomas theory. I should say that this is for mathematicians, this is a refinement of the strong rationality conjecture of Pandari, and Thomas. So okay, so it has its own place in Donaldson-Thomas theory, but to my knowledge, it's not proven, at least in the refined form. Okay, so this is what you get from here, and then perhaps I'll finish in 5 minutes. The last thing I want to say is that what's the evidence for this conjecture we formulated? So there is two types. I mean, there are two things that physicists can do when to get evidence for conjectures like this. One of them is direct computations. And we were successful in doing some direct computations to check this for rational curves with a single marked point. So that was done by localization using further conjecture, a K-theoretic index of Nekrasov and Okunkov. So that's one thing. So we can get evidence by direct computations. But we can do something perhaps more conceptual, at least from the physical point of view, which is try to use string theory dualities. So we can, in this particular case, M type 2A duality. And this is a sequence of dualities which is known in the physics literature as geometric engineering. It's geometric engineering. So there's a long history in physics, which I don't have time to get into. But there's a mathematical formulation of this sequence of dualities, which occurred in a recent paper of Nekrasov and Okunkov. I think, to my understanding, is still conjectural. Part of the paper is still conjectural. But there is a mathematical framework proposed by Nikita and Andrei concerning about this duality, for this duality. So how it goes is as follows. I'm just going to sketch it in a few minutes. I'm not going to give you the punchline. And the good news for us is that although perhaps it's not completely rigorously constructed, it does explain the occurrence of McDonald polynomials. So it goes like this. Okay, so this is, as I said, using recent work of Nekrasov and Okunkov. So I'm going to state it in this particular case. Okay, their work is more general, but I only need it in this particular case, which now we take a fivefold. That's going to look like this: OC twiddle plus OC twiddle plus OC twiddle plus KC twiddle over the curve, over the root stack C twiddle. And now this is a fivefold, and what they do is they conjecture the existence of a counting problem for membrane quantum states in M theory, which is a counting problem formulated on the fivefold. So there is going to be some counting, so-called M2 counting problem, which is in full rigorosity is going to be a very hard theory, I believe. But let's accept that exists. So there is some counting problem. And what now they do, what we can do using this, we notice that there is two torus actions here. There is a C star 1 and C star 2, both of them anti-diagonal. Okay, so there is two torus actions, and what you can do when you have torus actions like this, you start with this complicated counting problem on a 5-fold, and using localization, you can reduce it to a 3-fold problem. And if you use localization for the first torus, what you get is the dt/pt theory of, actually the pt theory of our x. It's a long story, but I'm being schematic here. And now if we do localization for the second torus, well, what we get is something like pt theory for a non-Calabi-Yau 3-fold, which is just C-twiddle cross C2. Okay, so you get a pt. It's all equivariant. It's a long story. So pt theory for this non-Calabi-Yau 3-fold. And now if you analyze this theory to employing some physics tricks along the way, from here with a lot of work, you can actually show that the partition function you get here, you get from this theory here. It's basically again given by this side of the formula up to change of variables. And the way this is done is by this arrow here goes exactly through to Haymann's construction for McDonald polynomials. So from here you get very naturally McDonald polynomials using Haymann's results. But I really don't have any time to go into detail here. It's a fairly long computation, and it's quite remarkable that at the end of the day, going through this 5-fold theory that's kind of mysterious, everything gets all parts click together, and we get, I think, a convincing evidence for this conjecture. And I think it's a good time to stop. And thank you very much. And okay, so I want to wish Maxim Hark happy birthday.
And actually, question, where is the character varieties? And it's the last part of your talk. You spoke only about Higgs bundles.
Yeah, so it got replaced by Higgs bundles, and the W filtration got replaced by the perverse filtration.
P double I. You're assuming P double I.
I'm assuming. I'm sorry. I should have stressed it. Yeah, I'm assuming P double.
We're using that actually.
How you use?
Well, when I
filtration, yeah.
Well, it's well, you see, there is further. Okay. Yes, there is. It's part of this refined Gopal-Kumar-Vafa expansion, because there is, even in 2000 when the Gopal-Kumar-Vafa appeared, there was work by Hosono, Saito, and Takahashi saying that the GV BPS invariants should be identified with the dimensions of the graded pieces in the perverse filtration on the cohomology of Higgs. Well, so this is a natural interpretation. In this side, it's a natural interpretation for GV invariants. Of course, their claim is true basically for smooth spaces, but under the circumstances, this is a smooth space. I mean, the moduli space is a stable Higgs bundle. It's smooth. So in this case, we can actually employ their definition and think of this as a mathematical definition for BPS invariants. It's very much in agreement to the intuitive picture of Gopal-Kumar and Vafa, because if you think how you compute the graded pieces here, you have this Lefschetz action by the vertical polarization, and that's really what it's in sync with physics.
Yeah, but when you use Nekrasov-Tokunkov, they have equivariant localization. How you compare it with
No, that's a further step. No, at the end of the paper, they also talk about refined invariants. You have to upgrade. Yes, I gloss over a lot of stuff. I agree, but yes, it's kind of you have to. In particular, they have this definition of refined invariants as a K-theoretic index. So it's not defined. They're identified with some K-theoretic index. I think, yeah.
Okay, more questions? Do you have any questions?
All right, so then let's thank Emanuel.
Thank you.